Molecules and compounds are formed when two or more atoms form a chemical bond with each other. For example, an example of a molecule would be something like carbon dioxide. And we can abbreviate carbon dioxide as CO2. And what that tells us is that there is one atom of carbon chemically bonded to two oxygen atoms. Some other examples of molecules and compounds include things like water. Water has the molecular formula of H2O, which tells us that it's made out of two hydrogen atoms and one oxygen atom. Some other molecules and compounds could be things like glucose. Glucose is a simple sugar, and it has the molecular formula of C6H12O6. And what this tells us is that there are 6 atoms of carbon bonded to 12 atoms of hydrogen, which is also bonded to 6 atoms of oxygen. So glucose is a molecule that's actually made up of 24 atoms that are all bonded together. So how do these atoms form chemical bonds with each other? And the key subatomic particle involved in chemical bonding are electrons. And we're going to talk about 3 different types of chemical bonds in this video. The first type we're going to talk about are covalent bonds. The second type are ionic bonds. And the third type are hydrogen bonds. Some atoms are more likely to form chemical bonds than other atoms. And the reason why this has to do with those electrons. So let's take a look at some examples of atoms that do not react with other atoms and atoms that do form bonds with other atoms. So first let's take a look at helium. If we were to look up helium on the periodic table, we would find that it has an atomic number of 2 and an atomic mass number of 4. And if you're not sure what these values mean, you should look at my other video that talks a little bit about how to read the periodic table and what the difference is between the atomic number and the atomic mass number. But what these values tell us is that helium has 2 protons. It has 2 neutrons, and we get that number from taking the atomic mass number minus the atomic number. So we get 2 neutrons, and we get 2 electrons. And we get this value because it's going to be the same as the number of protons. So if we were to draw a model of an atom of helium, we would put the 2 protons in the middle, in the nucleus, put the 2 neutrons in the nucleus, and we'll put a little dotted line to signify the nucleus. And then we need to draw the orbitals. And so remember, the orbitals are where the electrons are. So we'll start by drawing our first orbital. And remember that the first orbital can hold a maximum of 2 electrons, and helium has 2 electrons. So as I mentioned, that first orbital maxes out at 2 electrons. So because helium's outermost shell is full, it is non-reactive. So a full outer shell means it's non-reactive. This means that it's not going to react with any other atoms. Now we call this outer shell, this outermost shell is called the valence shell. So let's take a look at another example. Let's take a look at our good friend carbon. Carbon has an atomic number of 6 and an atomic mass number of 12. And remember, I just got these values from the periodic table. These numbers tell us that carbon has 6 protons, 6 neutrons, which we get from taking 12 minus 6, and 6 electrons, which remember, the number of electrons is just equal to the number of protons. So if we were to draw a model of carbon, we would put our 6 protons in the nucleus and our 6 neutrons in the nucleus. And we'll draw our little dotted line so we know that that's the nucleus, or the middle of the atom. And then we have to place our electrons. So in our first orbital or shell, remember it maxes out at 2 electrons. So we're going to put 2 electrons in that shell. But carbon has 6 electrons, so we still have 4 more electrons that need somewhere to go. So we're going to add a second electron shell. And in that one, we're going to add our 4 remaining electrons. Now remember that the first shell maxes out at 2. But the second shell maxes out at 8. And if we had a third shell, it would also max out at 8. So remember, the first shell can only hold 2, but every shell after that can hold a maximum of 8 electrons. Now for carbon, the valence shell is actually going to be the second shell. So the second shell here is the valence shell. So remember, the valence shell is just the outermost shell, and these are actually called valence electrons. And these valence electrons are the ones that are involved in chemical bonding. So if you look at the outer shell of carbon, it can hold a maximum of 8 electrons, but it only has 4 electrons present. So since the valence shell is not full, carbon can form chemical bonds with other atoms. So if the valence shell is not full, then it can form chemical bonds. Take a moment to quiz yourself to see if you understand how to figure out which atoms are reactive or likely to form chemical bonds and which ones are not. So I gave you 4 examples here, and I gave you the atomic number and the atomic mass number, which you could also just find on a periodic table. So I recommend that you pause the video, work these out, and then I'll give you the answers when you resume. All right, so hopefully you took my advice and you quizzed yourself. And now let's go over the answers. So let's take a look at neon. So neon has 10 protons, 10 neutrons, which we got from taking 20 minus 10, and it has 10 electrons. So to draw this, we would put our 10 protons in the nucleus and our 10 neutrons. Draw our nucleus around there. And then we would add our electrons. So the first shell would hold 2 electrons, which means we have 8 remaining. So our second shell, which remember can max out at 8 electrons. So we're going to put our 8 electrons in that second shell. So 1, 2, 3, 4, 5, 6, 7, 8. So our valence shell, which is our outermost shell, is full. Because remember that this shell can hold 8 electrons and it has 8 electrons. So neon is non-reactive, which means that it does not form chemical bonds with other atoms. So now let's take a look at boron. Boron has 5 protons, 6 neutrons, and 5 electrons. So to draw this atom, we would put our 5 protons in the middle, along with our 6 neutrons. And that's the nucleus of our atom. And then we're going to form our electron shells. The first shell can hold a maximum of 2 electrons. The second shell can hold a maximum of 8, but we only have 3 left because remember we have 5 electrons, and 5 minus the 2 that we put in the first orbital means we only have 3 left. So 1, 2, 3. Now our valence shell, remember, is our outermost shell. And it can hold a max of 8 electrons, but it only has 3 electrons. So do you think that boron is reactive? And the answer is yes. So boron will or does form chemical bonds with other atoms. Now I should have planned ahead and I have run out of room. So I'm just going to give you the answers to the other two so that you can double check yourself. So the answer for lithium is that yes, it is reactive. So it will form bonds with other atoms, whereas argon is non-reactive. So hopefully you went through the motions and you actually drew out those models and you're able to understand why they are or are not reactive. The first type of bond we are going to talk about are covalent bonds. And the way that covalent bonds work is that atoms share valence electrons with each other. So let's take a look at our good friend carbon. We talk about carbon a lot because this is biology and life is carbon based. So we're going to talk a lot about carbon and the bonds it forms and how it allows for life to exist. So remember that carbon has an atomic number of 6 and an atomic mass number of 12. And that information tells us that there are 6 protons, 6 neutrons, which we get from taking 12 minus 6, and 6 electrons. which we get from the number of protons present. So let's draw an atom or a model of an atom of carbon. So we'll put our 6 protons in the nucleus along with our 6 neutrons and draw our nucleus there. And then let's place our electrons. So we've got our first shell, which can max out and hold 2 electrons. So we add a second shell since we still have electrons that need a place to go. And we can put our 4 remaining electrons in this second shell. Now remember that this outermost shell is called the valence shell. And it has a maximum of, in this case, it has a maximum of 8 electrons because it's the second shell, but it only has 4 electrons. So this actually tells us something right here. It tells us that carbon can actually form 4 chemical bonds with other atoms. So let's take a look at how it would do that. So let's take a look at hydrogen. So carbon and hydrogen, they bond together a lot. So you oftentimes see carbon bonded to hydrogen. So with hydrogen, we have 1 proton. We have 0 neutrons because 1 minus 1 gives us 0. And we have 1 electron. So we can draw our hydrogen atom down here. So we're going to put our 1 proton in the nucleus. And then when I draw the electron shell, I'm actually going to overlap it with carbon. And I'm going to put hydrogen's 1 electron into that shell. And you'll notice how I have shared the electrons between them. So what I just drew here, this would be called a single covalent bond. Where each atom is sharing 1 electron with the other atom. Now in doing so, hydrogen is now totally stable because hydrogen now has the equivalent of 2 electrons in its valence shell. So hydrogen can no longer form any more chemical bonds. Carbon still does not have a full valence shell, but it is fuller than it used to be because instead of having 4 electrons in its valence shell, it's now sharing 1 of them with hydrogen. So we can get rid of that 4 and say that it now has 5 electrons. And the more electrons an outer shell has, the more stable it is. So carbon is increasing in its stability, even though it's not entirely stable yet, because its valence shell is not totally full. But we can still make 3 more bonds with carbon. So carbon still has 3 more valence electrons that can form bonds, and it has space for 3 more electrons in its valence shell. So we could add another hydrogen atom down here. So I'll put H for hydrogen, just to help us keep track of what we're looking at. So for hydrogen, we've got our 1 proton in the nucleus. And then we'll draw our electron shell and draw our hydrogen nucleus, or our hydrogen electron in that shell. And so now we have formed another single covalent bond, this time between carbon and this hydrogen. Now if we go over and look at our numbers for carbon, carbon now has 6 electrons in its valence shell, which means that it's becoming more stable, but it can still hold 8, it only has 6, so carbon can still make 2 more bonds. So do you think we could add a hydrogen here and a hydrogen here? Absolutely we can. So we can put our hydrogen, our one proton here. And we can draw our electron cloud, add our one electron for hydrogen, and now this hydrogen atom is stable, and carbon has become more stable because it now has 7 electrons in its valence shell, but it can still have one more chemical bond. So we could put a hydrogen up here. Add in our electron shell, add our electron from hydrogen, and now carbon has 8 electrons in its valence shell, so it is full. And by full, we mean that it's stable, and it's no longer able to make any more chemical bonds. Now, in sharing those electrons, each one of these hydrogens is also stable because it now has 2 electrons in its valence shell that has stabilized it. And just to recap, remember that of these electrons in the valence shell, remember that 4 of them came from the original carbon atom, and the other 4 came from the 4 different hydrogen atoms. But because they're sharing the electrons, both atoms are benefiting from that shared electron, and they're both becoming more stable. And the molecule that we just drew here is actually called methane. We can also write out methane as CH4 because it's made up of 1 carbon atom and 4 hydrogen atoms. We could also draw it out like this. Where each one of these lines represents one of those covalent bonds. And to give you kind of an example of what methane is, it's the primary gas that makes up your farts. It's also a gas that is produced as a byproduct of decomposition, and it's also found in things like natural gas, so we can burn methane in order to get energy from it. Covalent bonds can also form larger molecules. So let's take a look at another molecule known as ethane, and its chemical formula is C2H6, and this is also called ethane. And we could kind of draw this out in shorthand by drawing the 2 carbons bonded together, and then each carbon has a hydrogen attached to it. Now, if we were to kind of draw this out using our model, we could start with one of the carbons. So we'll start with a carbon here. Remember that carbon has 6 protons and 6 neutrons in its nucleus. And then we have 6 electrons that we need to place. So the first 2 electrons will go in the first shell, and the second, or the remaining 4, will go in the second shell. So remember, this outermost shell is known as the valence shell. And in order for an atom to be stable, the valence shell needs to be full. But in carbon, the valence shell can hold 8 electrons, but it currently only has 4. So let's draw another atom of carbon kind of next to it. Put our 6 protons and our 6 neutrons in the nucleus. In the first electron shell, we'll place our 2 electrons. And then for our second one, I'm going to have it overlap with the other carbon. And we're going to place one of those electrons there, and then the other 3 electrons. So remember, we have now formed a covalent bond between the 2 carbons. And that is actually indicated by this line right here. Now each one of these carbons still has spots open for binding, because remember, the valence shell can hold 8 electrons, and each carbon currently only has 5 because it's sharing these 2. So 1, 2, and then 3, 4, 5. So let's draw some hydrogens in there. So remember that hydrogen has 1 proton in the nucleus and no neutrons. And it only has 1 electron. So we will draw our orbital and put our 1 electron in there for hydrogen. And now hydrogen is stable because it's got its 2 electrons in its valence shell. And this carbon has become more stable because now it has 1, 2, 3, 4, 5, 6 electrons. So we can draw a hydrogen over here. And do the same thing with this hydrogen. We can add our electron cloud, draw our electron in there. And now this hydrogen is stable because it has a full valence shell. And the carbon is becoming more stable because it now has 1, 2, 3, 4, 5, 6, 7 electrons in its valence shell. So let's go ahead and finish this one off. So we'll add a hydrogen, add the 1 proton in the nucleus. Put our nucleus there, draw our electron cloud, add our electron in, and now this hydrogen is stable, and this carbon is now completely stable as well, because it now has 8 electrons in its valence shell. Now the carbon on the left here is still unstable. It can still form some more bonds. So we can go ahead and add our hydrogens in over here, following that same kind of example that we did before. Sorry, I forgot to draw my little nucleus in there. So now this carbon has 1, 2, 3. Sorry, I forgot to put the hydrogen electron in there. So it's got 1, 2, 3, 4, 5, 6 electrons in its valence shell. So we can add another hydrogen over here. So now this hydrogen is stable, and the carbon is becoming more stable because it now has 7 electrons in its valence shell. So we will finish it off by adding our last hydrogen with our 1 proton. And now all of the atoms are stable because hydrogen has 2 electrons in each of its valence shells here. And carbon is stable because it has 8 electrons in its valence shell, which is the second shell. So far, we've only talked about single covalent bonds. And a single covalent bond is just where 2 atoms each share 1 electron with each other. So this is similar to what we drew with our methane, where we drew our carbon bonded to our hydrogens. And in each of these covalent bonds, carbon was sharing an electron with hydrogen, and hydrogen was sharing an electron with carbon. Now, it's possible for atoms to share more than one electron with each other. So in a double covalent bond, each atom shares 2 electrons with another atom. So for example, we could have something like a carbon double bonded to another carbon, and then maybe some single bonds between carbons and hydrogens. So for an example of this, we could draw a couple of carbon atoms with the 6 protons and 6 neutrons in the nucleus. Our first electron cloud with 2 electrons, and then our second electron cloud with the 4 remaining electrons, but I'm actually going to draw 2 of them over here. And then the neighboring carbon would look very similar with the 6 protons, 6 neutrons in the nucleus. Our first shell maxing out at 2 electrons. And then our second shell is going to overlap the shell of the carbon. And now we're going to put 2 of those electrons there. So to help you kind of keep track of where these electrons came from, this carbon has the 1, 2, 3, 4, 5, 6, we can say there. And then this other carbon has the 1, 2, 3, 4, 5, 6. But you can see that we're now sharing 4 total electrons, or 2 each, in order to form that double covalent bond. Whereas in the single covalent bond, we would only have 1 pair of electrons being shared between the 2. And then we could draw our hydrogens in there, but for sake of time, we are not going to do that right now. So you've probably figured out that with a triple covalent bond, each atom shares 3 electrons with another atom. So you can imagine that if we were to draw this out, it would look something kind of like what we see over here. But there would be 6 total electrons, 3 from each carbon, being shared with the other carbon. And so we can actually draw that out shorthand like this. And then we'll go ahead and put some hydrogens in there to make our carbon stable. So this would indicate our triple covalent bond. Now, the more electrons an atom shares with another atom, the stronger that bond is going to be. So when we're looking at covalent bonds, the strongest is going to be the triple, and then the weakest is going to be the single. Now, all covalent bonds are still relatively strong bonds, but the more atoms that are being shared, just the stronger it's going to be. There are different types of covalent bonds, and we can call those nonpolar and polar. And it really comes down to how evenly the electrons are being shared between the 2 atoms. So in a nonpolar covalent bond, the atoms in the molecule share electrons equally. So far, all of the examples we have looked at, so the methane and the ethane and ethylene and all those other examples that we've looked at, we were looking at non-polar covalent bonds. So I like to think of this as kind of sharing a blanket, okay? So if you're snuggled up on the couch with someone and you have a blanket that you're both kind of sharing and you're sharing it equally, and then you're both benefiting from that blanket and you're kind of snuggling up together and everything's good. Now, in a polar covalent bond, atoms do not share the electrons equally. And this is more of a situation in which you're trying to cuddle with someone under a blanket, and the other person is stealing the blanket from you. So you maybe only get a little piece of the blanket, and the other person is getting the majority of the blanket. So in both cases, you're sharing the blanket, but it may not be totally fair as to how much of it or how you're sharing that blanket. So let's take a look at our methane again. Okay, so remember our methane was just a carbon atom. So here we'll say methane, example. Remember methane is just CH4. So it's a very simple molecule. So we can kind of draw it in shorthand where we can put our carbon atom in the middle, and then we can just draw our 4 hydrogens attached to it. So you'll notice in chemistry that you'll start to get very lazy as to how you draw things. So you could draw out those big models that help you understand how the bonding is happening and the valence electrons. But once you get that concept, you start drawing things like this, or even just kind of like this. So the CH4 is a very lazy way of writing it down. So as you can see here, methane is a non-polar molecule. And that's because each hydrogen is equally sharing its electron with an electron in carbon. Now let's take a look at an example of a polar molecule. And the example we're going to use is water. And the molecular formula of water is H2O. So let's draw this molecule of water out since we haven't looked at it yet. So if we were to take a look at oxygen, oxygen has an atomic number of 8 and an atomic mass number of 16. So that tells us that oxygen has 8 protons, 8 neutrons, and 8 electrons. So to draw a molecule, or to draw an atom of oxygen, we would put our 8 protons in the nucleus along with our 8 neutrons. And then we'll place our 8 electrons. So in our first shell, we have 2 electrons. And then in our second shell, we're going to have 6 electrons. So 1, 2, 3, 4, 5, 6. Now to add in our hydrogens, so we've got 2 hydrogens in this molecule of water. And remember that hydrogen has an atomic number of 1 and an atomic mass number of 1. So it's got 1 proton, no neutrons, and 1 electron. So we will draw our first hydrogen down here. We'll add our 1 proton in there. And then we'll overlap our electron orbitals and put our shared electron in there. Sorry, I forgot to draw the little nucleus around my hydrogen. And then we'll draw another hydrogen down here with our 1 proton. Add our nucleus. And then we'll overlap our electron shell and fill it in with that electron from hydrogen. So now oxygen has a full valence shell because it's got 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is now stable, and both of the hydrogens are now stable because they have the 2 electrons in their valence shells. And so what we have here are single covalent bonds between each hydrogen and the oxygen. Now, oxygen has a property known as electronegativity, and all atoms kind of have this value of electronegativity. And what that means is that oxygen is kind of greedy when it comes to electrons. So I know so far we have kind of drawn these electrons as static and just kind of being in this one spot in this orbit surrounding the nucleus. But in reality, these electrons are constantly rotating, and they're actually kind of orbiting the nucleus in 3 dimensions. So these electrons are constantly moving around in these orbitals. And these shared electrons are spending some of their time with oxygen. So they're spending some of their time here with oxygen, and then sometimes they go hang out with hydrogen. And same thing over here, where sometimes those electrons are orbiting oxygen, other times they're orbiting hydrogen. Now, because oxygen has this electronegativity, it means that it's kind of greedy and it holds on to those electrons more often than it lets hydrogen have them. So essentially what happens is that oxygen starts to take on kind of a partial negative charge. And that's because it now has kind of extra electrons orbiting it. So it has its 8 protons in the nucleus, but at times it has more than 8 electrons rotating around it. And because of its electronegativity, it has those electrons more often than it gives it or allows hydrogen to have it. So what we end up with is that oxygen takes on kind of a partial negative charge. So what we end up with is that oxygen takes on a partial negative charge. Now, hydrogen, because it has its 1 positively charged proton, but at times it has less than 1 electron. So at times it doesn't have any electrons because those electrons are going and hanging out with oxygen. And so hydrogen starts to take on a partial positive charge. So to draw this out in kind of a simpler way, we could have our oxygen atom bonded to our 2 hydrogen atoms. And then we use this little symbol to indicate a partial negative charge on oxygen. And then that same symbol, but with a plus, to indicate a partial positive charge on hydrogen. So this symbol right here means partial positive charge. And this symbol means partial negative charge. So essentially what we end up with is a molecule that has a positive end and a negative end. So it has poles to it, which is why it's called polar. And you can kind of think of these molecules as acting like magnets. So if you remember back from, elementary school maybe when you were learning about magnets, and magnets have a positive end and a negative end. And that's what happens with these molecules. And it actually affects the kind of the reactivity or how these molecules behave. So non-polar molecules are going to behave in a different way than polar molecules. And we'll talk about that a lot more when we talk about things like the cell membrane and how different molecules interact with the cell membrane. We'll also talk about how this polarity gives water some very kind of specific properties that help it be conducive to maintaining life. Now, there are other polar molecules that exist, but especially in biology, we really focus on water because water's polarity is essentially what allows life on Earth to exist. So, learning about polar covalent bonds producing these polar molecules leads us into the next kind of bond that we're going to talk about, which are hydrogen bonds. And hydrogen bonds exist between polar molecules. So let's take a look at our water molecule that we learned about on the previous page of this presentation. So remember that water is H2O, which means it's made up of one oxygen atom bonded to two hydrogen atoms. We can draw it like this. It kind of looks like Mickey Mouse. And remember that the oxygen has that partial negative charge, and the hydrogens have the partial positive charges. And that's just because remember that the electrons are hanging out with oxygen more than they are with hydrogen. Now, if we were to put a couple of water molecules near each other, so let me draw a couple more. You'll notice that we have some charges that are potentially hanging out with each other. And we know that opposites attract. All right, so you can think of the magnet example where the opposite ends of a magnet are attracted to each other. So what happens is that the partial positive charges on the hydrogens are attracted to the partial negative charges on the oxygens. And what that means is that essentially a bond forms between the two. The same thing happens between the hydrogens and oxygens of other water molecules. And so these attractions are known as hydrogen bonds. So a hydrogen bond is just an attraction between the partial positive charge of one atom in a molecule and the partial negative charge of another atom in another polar molecule. And we're going to talk more about some of the properties of water, and we're going to talk a lot about the polarity of water and the hydrogen bonds that form between water, because this is really what allows life to exist. Now, hydrogen bonds, generally speaking, are fairly weak. You can actually break them with your finger. So if you've ever looked at a glass of water, and if you were to fill up that glass with water all the way up to the top, you've maybe noticed that you can actually fill up the glass a little bit above the top of the water. And the reason why that happens is because of the hydrogen bonding. And we'll talk about that a little bit later, but that is known as surface tension. Now you can easily break that bond just by poking your finger into the glass of water and making the water spill out. The third type of bond that we are going to talk about are ionic bonds. And ionic bonds are formed between an element that is a metal bonding with an element that is a nonmetal. And ionic bonds form in molecules that are called salts. Now, the most common or maybe most recognizable salt is what we would more specifically call a table salt. So table salt, this is the salt that is in a salt shaker on your table that you can add to food to make it taste better. Table salt is actually called sodium chloride, and we can abbreviate that as NaCl, also called sodium chloride. And it is made up of one atom of sodium and one atom of chlorine. So if we were to look at the periodic table at sodium, which is Na, and chlorine, sodium has an atomic number of 11 and an atomic mass number of 23. Chlorine has an atomic number of 17 and an atomic mass number of 35. So remember, that means that we can figure out how many protons, neutrons, and electrons each one of these atoms has. So an atom of sodium has 11 protons, 12 neutrons, and we got 12 because we took 23 minus 11, and then 11 electrons. Chlorine has 17 protons, 18 neutrons, which we got from taking 35 minus 17, and then 17 electrons, which remember is just equal to the number of protons. So let's start by drawing a model of an atom of sodium. So if we take our sodium, we would put our 11 protons in the nucleus along with the 12 neutrons. We would then put our 11 electrons into the orbitals. So our first orbital would have 2 electrons. Our second orbital would have 8. But that only gives us 10 electrons, and so sodium needs a third electron shell, which is going to have just 1 electron in it. Now let's draw our chlorine atom over here. So our chlorine would have our 17 protons in the nucleus and the 18 neutrons. And then to draw our orbitals, our first orbital would have 2 electrons. Our second one would have 8. Which gives us 10 total electrons, but we need to place 7 more. So we'll draw our third orbital and put 7 in that one. So remember that for these atoms, the outermost shell is the valence shell. And in both of these cases, the valence shell can hold a max of 8 electrons. Now for sodium, the valence shell only has 1 electron, which means it needs 7 more electrons in order to be stable. Chlorine, the valence shell, has 7 electrons, which means it only needs 1 more to be stable. Now, sodium could try to go and find 7 more atoms to form chemical bonds with in order to become stable. But that's a lot of atoms that would get very crowded very quickly in order to kind of gain that stability. Now, chlorine only needs one atom, and so it turns out that there's kind of an easy solution to this problem, and that is that sodium takes its valence electron and just gives it to chlorine. In doing so, chlorine now has 8 electrons, which means that chlorine is stable. Sodium has essentially gotten rid of its valence shell altogether because it got rid of the 1 electron that was in its valence shell. So now sodium's new valence shell is the second shell, which can hold a max of 8 electrons, and it has 8 electrons. So what we have here is kind of a win-win situation in which both sodium and chlorine became more stable because sodium got rid of its kind of unstable valence shell by giving away its electron, and chlorine gained the stability by gaining that electron. We have to do some accounting now though, because sodium has 11 positively charged protons, and it now only has 10 negatively charged electrons. So if you take 11 positives and 10 negatives and put them together, what you end up with is a charge of +1. So with sodium, we often just add a little plus sign next to it. Chlorine has 17 protons, which are positively charged, and it now has 18 electrons. So if you have 18 negatively charged particles hanging out with 17 positively charged particles, what you end up with is a charge of -1. And so for chlorine, we put a little negative sign next to it. Now we know that opposites attract. So you have a positively charged atom and a negatively charged atom. And so what happens is that they kind of hang out together because the charges attract each other. And that is called an ionic bond. So we talked about ionic bonds, and remember that ionic bonds form in these molecules that we typically just refer to as salts. And the example we used was table salt, which is sodium chloride. And what we ended up with was a sodium atom that was positively charged because it gave away one of its electrons to chlorine, which became negatively charged because now it has an extra electron, and those charges kind of hold them together like magnets, and that's our ionic bond. Now there are other examples of salts though. So table salt is, like we said, the most common, kind of the one that we're most familiar with, but anything that's held together by an ionic bond is called a salt. So we can also have things like magnesium chloride. We can have potassium chloride. We can have calcium chloride. So anytime atoms are held together by an ionic bond, it is known as a salt. Now the individual atoms in these ionically bonded compounds are called ions. And so an ion is just a charged atom. So for example, we have Na+, which is just a positively charged sodium atom, and we have Cl-, which is a negatively charged chlorine atom. Now we can go a little bit more specific, and cations are positively charged ions. For example, Na+, and anions are negatively charged ions. For example, the chloride, Cl negative. And one way that I remember the difference between the two is that if we look at cations, it has the word cat in it, and it is positively charged. So cations are positively charged, anions are the opposite, they're negatively charged. So in summary, we talked about three main types of chemical bonds in this lesson. So the first type we talked about are covalent bonds. Remember that covalent bonds can be single, double, or triple. The bonds can also be polar or nonpolar. And with covalent bonds, remember that it just means that atoms are sharing electrons. We also learned about hydrogen bonds, which are the attraction between polar molecules. We talked about ionic bonds, in which one atom gives an electron to another atom. We also talked about how some elements are non-reactive. And we actually talked about that at the very beginning. And then last but not least, I just want to take a look at the relative strength of these different bonds that we talked about. So the strongest bonds are going to be our covalent bonds, with the triple bond being the strongest of the covalent bonds. So triple covalent bond is the strongest, followed by a double covalent bond, followed by a single covalent bond, ionic bonds are kind of in the middle, and the weakest would be the hydrogen bonds. And when we talk about strength, we're really talking about how hard it is to break the bond.